I was just
Okay, any questions?
Derek.
Go ahead.
Derek, I just have a question, and maybe Pierre can answer it. He said that the first thing they do is try and disprove one another's theory. Now, I cannot, for the life of me, imagine how anyone can test an accuracy to 1 in 1 trillion. Because that's what you'd have to do in order to disprove a theory. Maybe Pierre knows.
Yeah, this is a thing of scale at that small, tiny scale, I think. Pierre, can you enlighten us on that incredibly accurate figure? How do they achieve that? It's mind-boggling.
I think it depends on the nature of the experiment and the measurement that you do. Electromagnetic waves are very, very small or short wavelengths. So small differences between electromagnetic phenomenon are measurable, but it is mind-boggling. I agree with Elaine.
Yeah. I mean, what sort of a voltmeter or whatever do they use to measure that? I mean, I can hardly see a millimeter on a scale. How can you see 1/1,000,000th of a millimeter? I suppose it's all sort of scanning electron microscopes and stuff like that. I don't know. I'm trying to imagine the instrument that can measure that. It's not a ruler.
Well, if you think of the size of the Large Hadron Collider, then you get an idea why it can generate such high energies and determine such small differences.
Yeah, I suppose. And Pierre, while you're on the line, that whole renormalization thing they're talking about to get the formulas to show the right prediction, which coincides with observation. I'm not very comfortable with that, but I mean, I'm not scientific enough to say why or what. Are you happy with how they achieved that, or was it like a sort of cheat or so on that it sounds like?
I think it was sort of forced on physicists to avoid infinities. The ultraviolet catastrophe, which was eventually solved by discreting by, what is it, quanta Hertz, saying that electromagnetic radiation is emitted in parcels, not continuous waves.
Okay.
And I think that was the first successful example of renormalization to prevent what was known as the ultraviolet catastrophe, which basically said that the shorter the wavelength, the more the energy it carries away. So, but renormalization was forced. Feynman, I think, was the one that was most famous for that, adding up all these Feynman diagrams, all the possible paths between two different states. But I think it's a mathematical trick to explain what you meant.
Pierre, when you were studying quantum physics, did they also give this sort of a logical flow of how things evolved and were developed, or did they just throw facts at you and you had to learn it and make sense of it? Because the way they present this is, I think it's fantastic. If this sort of method could be used in the classroom, it would have helped me a lot in the past. Was your experience in learning, or can't you remember that, anything like this, or was it just?
No, I think it's a question of timing. What make these lectures interesting is they've got the holistic view from Newton, basically, further on.
Yeah.
When in my student years, I mean, they could explain what was known at that stage, and quasars were the hot thing, and lots of debate about exactly what it was. and quarks are just recently been modeled. So the perspective in those years is totally different from a
Yes.
perspective now, where a lot of new knowledge has come to the fore. So I think the picture that you paint depends on when you actually paint it.
Yeah, a lot of the stuff in this video actually, I may have heard of some of it before, but I think there's a lot that's actually new to me. This whole thing of that double hydrogen alpha line. Maybe I've heard of that before, but I can't remember hearing about it. So it's all very interesting, you know. It's like hearing it for the first time, and having it explained properly, I think helps. Anybody else?
Yes,
Go ahead.
there where they mentioned that the electron must be spinning at even more than the speed of light. That throws a little wobble in the question. But my initial question was, how did they relate electricity and magnetism to generate electricity? When did that step come in?
Yeah, look, on the spin, I think I think what they were saying is that it's not a real spin. If it was, then it would be spinning faster than the speed of light. But it's not actually spinning. It's Pierre, perhaps you can clarify that. I don't know if you've got any. The thing of relating the magnetism to electricity, that was sort of, I think, probably some insightful perception by people in the 1800s. Just observing, sort of doing stuff and observing the effects that it had on other stuff and so on, and then trying to explain it.
It was most likely battery power or chemical generation of electricity rather than magnetic, like in direct current, not alternating current.
Yeah, of course, they would have had to invent magnets and generators and electric motors before they could generate electricity. I'm not sure at what stage that was. I think that was in the late 1800s. Yeah, Pierre, any comment on correcting my comment on the so-called faster than light spin of an electron?
Well, what I want to add is that it's a question of there are different characteristics. You've got to attach a name to it. It isn't actually an electron spinning in one direction and the other direction. You explain it in that way. Same as you've got the names of quarks, up, down, charm, and all the rest of it. It's just names. They're different characteristics which you have to give names to. You can call it anything you like, but there are different characteristics. And the moment you can distinguish between them, you must give them separate names.
Yeah, so I think that is what he said. He explained it as it's not being a real spin, it's just a name given to a parameter.
Yeah.
But not faster than the speed of light.
It's not spinning. It's not spinning, so it doesn't. So that's not. It's not so speed of light is actually not a consideration, not a problem.
Yeah. Okay. I'll be the speed of light.
It's not. It's not really spinning. It's just called a spin.
No. No, I mean it's been.
I mean it's like later on in this video they're going to give things colors as a differential description, but they don't have real colors. It's just a name.
Yeah.
I think quarks.
Yeah. Lovely. Thanks.
Okay. Have we got more comments, questions?
Hi, Derek. Yeah, I've just got one question. I'm trying to get my head around the notion of virtual particles. I can understand how maybe an electron can pop into existence if there's a anti-electron that also pops in at the same time, just to conserve, the neutral nature. But what are the other particles? I can't see how maybe a hydrogen atom can pop into existence with a anti-hydrogen, if you like, because an atom consists of, well, a proton, which is more than just one particle. It's what is it? It's two up quarks and one down quark. You'd have to have three things that pop into existence at the same time. I'm not sure if I'm making myself clear, but I'm just trying to understand what virtual particles.
I think on the level of an atom, an atom doesn't pop into existence. It's definitely only subatomic particles. I don't know, Pierre, is it a photon? Is the quark that pops in and out? I know that actually for example, within a proton, it's supposed to have 3 quarks, but sometimes it actually has 5 quarks and sometimes 8. So there are virtual quarks appearing and disappearing even inside a proton.
Well, I didn't think quarks could actually exist in isolation. You can't have just one up quark on its own. That was my problem in understanding the virtual particles.
Yeah, okay, Pierre, so what are the main virtual particles? I mean, they appear and disappear for a fraction of a second, I think.
I'm now speculating. I must be very careful. I'll read the transcript carefully. But I think the way to explain fluctuations in whatever field you're looking at, one way of doing is the exchange of vertical particles, which if you think back to Pierre Hugo's lectures on cosmology, I think there the virtual particles, or exchange of virtual particles, acted like an extra force giving energy sort of to the background fluctuation of whatever field you're talking of, the electromagnetic field or the Higgs field or whatever. So my simple reconstruct of that is that the fluctuations are explained by popping in and out of virtual particles which annihilate each other and give off energy. I think that's the main thing, give off energy.
Well, as I heard it, I think that virtual particles are actually required to explain the observation differences that they had compared to the theory prior to incorporating virtual particles, and it actually cancelled out infinities and those sort of things very nicely. I mean, that measurement that they found, that was they predicted it using the mathematics of virtual particles and came very close to within a very tiny difference of the actual observation. So yeah, some excellent questions there from Peter Kuho.
Yeah, I must have a think about this myself.
So
I obviously need to read a little bit more about it to understand it better.
Yeah, we need to go to AI or Google or something and ask it what kind of particles form virtual particles. But it's the only way of explaining a lot of stuff that was, observed.
Yeah, that's it's a fundamental understanding. That's what bothers me. If I can't understand the fundamentals, I'm finding it difficult to make a jump to the next step, I suppose.
Yeah, it's a good. So we need to sort that out before we really understanding and knowing, and the answers to your question will help us understand the rest of this series. So, Pierre, can we ask you to give us the right comment on that as far as you can at some stage for the next meeting?
Sorry for putting you on the spot there, Pierre.
Pierre, did you hear my question?
Sorry, I forgot to put on my microphone. I will read up more and I will comment further, but if I just Google what are virtual particles in physics, they are short-lived theoretical particles that mediate forces and cannot be directly detected, unlike real particles. They arise from quantum field theory as a way to describe interactions and are permitted to briefly violate the laws of physics by Heisenberg's uncertainty principle. They are not truly real particles with a definite mass and lifetime. They produce measurable physical effects such as force between charged particles, exchange of force. But I will read more. But
Yeah,
just
it's very interesting.
also describes it quite interesting, the mediators of forces and quantum fluctuations. So, but I will read up more about it.
Yeah. Okay. Thanks, Pierre.
So Peter, they have to exist, and if they just remained as a particle, that might be a problem. But they pop in and out. They're there and then they're not there. So they're sort of violating sort of energy balance, if you like, for a fraction of a time. But then they are bouncing back the other way. You know.
Yeah. No. As I say, I'll have to have a
So
read about it.
for a very tiny slice fraction of time, they are violating, but over a period of time, before and after they pop in and out, the balance is still zero. So they're both illegal and legal at the same time.
Okay. Thanks a lot.
Any case, if you just Google what are virtual particles in physics, you get quite an interesting and
Yeah, I think I need a couple of years at varsity as well, but I'm a bit too old for that.
Oh dear.
I hope you got your video on. You want to ask a question?
No, I want to hide among all this knowledge.
Well, it is quite intense, but you know, you sort of get a thread through it as well that I haven't really heard before, and it gives one a feeling. Yeah, this, you know, it feels like we're so close to answering this question of the unity sort of theory of everything. You know, it just feels like mankind's just got to take one little step and add in one more thing, and we'll have it. You know?
I think, Derek, the way I understand renormalization is in science you can equate anything to anything and add a constant and get away with it.
Yeah, I'm not sure exactly what they did, though. They didn't go into that detail, so you can't argue with something that they didn't mention. But Pierre seems happy with what they did, so we'll take his word for it. And I think, you know, people like Feynman got Nobel Prizes for these things, and probably it was convincing.
Yeah, significant. Thank you.
Yeah.
Sorry, another question is, it should be, I hope it's a simple, understandable answer, is if you break a bar magnet, you can't, the polarity changes, or you can't put them together the same way they broke. They repel each other.
Yeah, so if you have the bar magnet and you break it in half along its length, then the end that is opposite the south end of the old bar magnet will be north, and the end that is opposite the north end that broke off will be south. So they form into two new bar magnets with their own north and south. So where you broke it, they would snap towards each other.
No, they don't.
They don't.
No, I don't
Have you done that?
But
well, that's the way I would expect it to work. But if it doesn't work like that, then I'd need another explanation.
Yeah, I think your explanation is correct.
What was that? Sorry, they won't snap together again.
I think Derek's explanation is correct. If you break it in half, say north was on the left side of the original magnet, you break it in half, then at halfway, you'll get a new south pole. And adjacent to it, you'll get a new north pole to oppose the south pole on the right-hand side.
No, I don't think it works like that. Yeah. If you break any magnet, I think like a speaker magnet, a round one, a ring, I think if that breaks in half, you can't put them together the same that they were. I'm not sure about the
Look,
polarity.
if you think of it, just to keep it simple, a bar magnet, if you think of it, a whole lot of little elements that are lined up, okay,
Yeah.
and each one has got its north and south.
Yeah.
And all the atoms, the ferrite, whatever atoms, lined up in one direction magnetically, make the whole thing a magnet. So if you break it in half, those are all still lined up in the same direction in each half. So you still get a north and south in each broken part, and you'll have the opposite poles will be at in the two faces of the ends that were broken apart.
Yeah, no, well,
so they will still, the two ends that were broken apart will still magnetically attract each other.
Yeah, no,
So do a diagram of it and you'll understand it better.
Yeah, no, I can understand that logic, but I seem to remember it didn't seem to work like that from way back.
Yeah, there may be some other aspect that you're thinking of. I don't know.
I'm very sure I couldn't put them together the same way that they're broken. I think a round speaker magnet, a ring, I'm not sure of the magnetic field of that, whether the inside is south and the outside is north, or whether the one side of the disk is north and the other side of the disk south, I'm not sure. But yeah, I'm sure I had broken a magnet and it wouldn't stick together again the same way that it had broken.
Sorry to interrupt. I was just thinking if there's a disk magnet, the top surface would be like, say, north, and the underside would be south. And if you broke it into two semicircles, you would still have two north on the top and two south on the bottom. And when you tried to push them together, you'd be trying to push a north against a north and a south against a south. Does that maybe explain it?
That's something like that, yeah. But,
yeah, I don't know. I'm not an expert on magnetic, but I imagine that, and if you have is a speaker magnet? Is the ring or is it a solid circle? I don't know.
No, ring.
It's a ring. So I imagine in a ring that the field, electromagnetic field around the ring would also be donut shaped. So you'd have the field lines sort of going in circles around the ring, if you understand what I'm saying. So you'd have actual north would be, for example, outside, and south would be on inside the ring.
Yeah. Although if you see the copper coil is mounted in the middle of the hole in the ring for the speaker. So it might well be a north one flat side and south the other flat side for the coil to move the
Okay, we'll have to get you to take a video of with you going with an axe and chopping up a speaker and showing us what happens to the magnet.
I'll do that part, yeah. But the explanation, I'm not sure. But as I say, even I think with a bar magnet, I seem to remember many years ago that I found a broken one, or there was a broken one, and I tried to put it together as original, but it was repelling each other all the time, so it would flip around. And
interesting.
Yeah.
Sounds like a good topic for a YouTube short.
Okay, yeah, I'll bring out my big axe if I can find it. Great stuff. Thanks very much. It's been
our pleasure. All right. Any more comments from anybody, or can we wrap it up? All right. Thanks everybody very much for your attendance. And Peter, I see you had trouble trying to get the message through to ASA members.
Yes.
Maybe if that happens again next time, just have you not got the emails of the usual attendees? Like
no, I haven't. I actually looked for them.
So on like that.
Yeah, no, I looked for them and I don't have their emails, their individual emails, because I've always depended upon the VIP. And the reply from Lerica regarding my query on it, she just referred it to AJNL, and it seemed that AJNL hasn't renewed the subscription or whatever is required. And that's what I gathered from that. So I don't know. Presumably, I tried again tonight, and I also got a bounce back. So I don't know. Presumably, some stage it'll be sorted out.
Yeah, that's a
Hopefully.
pity, because I think there's 4 or 5 of the guys that attend on a regular basis would have been interested in this one.
Yes, absolutely.
Okay, thanks very much for your attendance, and enjoy your supper, and we'll see you next time.
Thanks.
Thanks, Rick.
Good night,
Thanks, everybody.
Bye, everybody.
Yeah, good night.
Right. Right.